long journey. I mean, we have started working almost in 2006-7, and then I thought I will give a glimpses of my journey, our journey for with which started with my professor, Professor Siddiqui, and then in my journey, different collaborators in the form of Professor Yahya Antar, who is incidentally current Antenna Propagation Society President, and then Dr. Ashin Iyer, who's from University of Alberta, and then my own students. Few of them have already graduated in PhD, and few are in different states of their PhD. So I thought I'll give you a glimpses of the overall activities that has happened in our years for last 15 years. And very recently, we have taken some new initiatives where some young researchers, some of my students, and some of my collaborators like Dr. Sarkar, Devdeep Sarkar, and others are contributing. So considering the fact that there might be some widespread participants, as a customary, I show this slide everywhere. That's our institute, which is at the southern tip of Kerala. Okay. Incidentally, the organizers and we both are in the western coast. And this institute started its journey in 2007 under the leadership of Kalam, which is called the Missile Man of India, and later on the President of India. The goal of this institute, I mean, the motto was basically to create quality human resources for Indian space research organization, and of course, one of the first space institutes or universities across the globe, and definitely first in Asia. I mean, we are proud to say that this institute has produced close to 1,000 ISRO scientists, and they are deployed in different centers of ISRO, starting from the center where today's chief guest comes from, ERL Satellite Center, then Space Application Center, Ahmedabad, and other centers, and so on and so forth. So we are a pretty new institute, starting our journey in 2007. So I see some noises, background noises. So if you are in front of the system, kindly mute yourself. So before I go into the agenda, which is a journey on metamaterials and its applications over a decade, I just take maybe a couple of minutes or so to introduce you about the different kind of research activities that's happening in our group. We predominantly work on the printed antennas, where different candidates starting from ultra widebands to some other kind of structures. Under this category itself, these metamaterial inspired antennas come into picture. And as I mentioned, being a part of Indian space mission, and being a part of IIST, we are having a very strong collaboration with different ISRO centers. So we design different kind of antennas for ISRO's requirement and applications. Also, one of those fruitful collaboration is with National Remote Sensing Center, Hyderabad. Then we are in touch with Space Application Center, Ahmedabad, also on terahertz kind of activities. And then this is the third wing of our research, which have started recently. We are concentrating on wireless energy harvesting, wireless power transfer, and some kind of optical fiber based sensors, which are not directly linked with metamaterial, but which are more or less like optical fiber based different kind of sensors for biomedical applications. So
Sir,
this
your
is,
voice is very low. The participants are requesting a little bit louder.
I am audible. Dr. Saha is audible to me.
Yeah, you are audible, but voice is
I
very low.
I am increasing my system volume to the maximum possible now. Uh, is it
Yeah,
better
it's
now?
okay.
Yeah, sir, now is good.
Okay. Okay. So please do the same activity again so that I mean, I don't hear anyone else. Okay. Yeah. Is it fine?
It's now good. Sir.
Yeah. Yeah. So as I mentioned, I'll take another couple of minutes or so to introduce the different kind of activities that's happening. I'll be a little bit fast because on some of the slides, I'll be going into the details later on. So these are some of kind of antennas which we called printed antennas, but these are some metamaterial inspired antennas. I mean, as you can see, some of those works are published in IEEE transactions and letters and so on and so forth. So these are basically very simple technique of, loading different kind of filters into the feed section of the antenna. And incidentally, those filters are inspired from metamaterial structure. But unfortunately, we don't call them metamaterial antennas because it is not wise or it's not correct to call them metamaterial antennas, because you just use a elements or a pair of elements of split ring resonators or different kind of switches or copper wires to mimic different kind of switching action and to realize different kind of resonators that can be used sometimes for radiation enhancement, sometimes that can be used for creating frequency notches, and then we have used those kind of antennas for realizing different kind of complementary functionalities. We have named them as so, I mean, these are metamaterial inspired structures, but again, these are not metamaterial antennas. And then, as I mentioned, due to our strong collaboration with different space centers, ISRO centers, and also with collaboration with some CSIR labs like NIIST, which is also at Trivandram, we do some work for space antennas and also dielectric resonator based antennas. So this is a strong wing that's going on as of now. So this slide I'll be skipping because I'll be going into some of the detailed activities. So these are some kind of filter integrated antennas. As you can see, different variants of antennas, not only the UWB antennas that I just showed, but also we have tapered slat antennas and then horn antennas and some other kind of dual antennas. I mean, cognitive radio applications kind of thing where we have ultra wideband and a narrow band antenna, and there are some techniques for enhancing the mutual coupling between the antenna elements. This is a very interesting piece of work on which I'll be going details. That is the antennas for applications. This is a the front page of our article on antenna advanced in cognitive radio, which appeared in 2018, pretty recently, I would say. And here I'll be going into the details of how using the metamaterial inspired structures in the form of split ring resonators and different kind of switches, you can come up with some fascinating applications. So this is again the continuation of that, as I mentioned, and this is what I mentioned, some collaboration and some work we have started in terms of terahertz antennas. So one of the techniques for producing terahertz signals is to design photoconductive antennas, and interestingly these antennas are designed on semiconductor electric substrate, and these antennas are actuated by applying the laser beam. So you basically apply a laser beam of proper wavelength, so that the photon energy h nu is sufficient enough to interact with the semiconductor. That means the band gap and the photon energy are matched. Then it creates a transient current, and that transient current causes radiation. As far as this particular wing is concerned, we are not fully dependent as of now, because we need to have very strong collaboration with people who are having VLSI fab facilities, and you also have to have the photonics concepts, I mean photonics equipments and all, to test this kind of antennas. So we do collaborate with space application centers and then some other IITs also and ISR also on this kind of research. So these are some of the antennas that we have designed using this collaboration with space application center. These are many hundred times magnified view, because these are in the micron and nanometer length. So these are some kind of antennas which are realized on gallium arsenide and its different variants, mainly the LT gallium arsenide or semi-insulated gallium arsenide, and some of the equipments, as you can see, that is required for realizing this kind of antennas in a clean room environment. This is another wing of our research, which is on very recently started, in fact, during the collaboration with Royal Military College of Canada, which is basically, dielectric resonator based wireless power transfer. I'll be very brief because I have a couple of slides on this particular thing. And as I mentioned, we do some kind of space antennas also. So this particular second part of the slide below this, I mean this, as you can see probably my mouse pointer, this particular antennas is in collaboration with National Remote Sensing Center, Hyderabad. The goal of these antennas is to design, satellite tracking, and so that we can track the satellite and we can effectively receive the data from the low Earth orbit satellite. So this a part of the work we recently published in IEEE, and some other ongoing work I'm not going to disclose now, but we are doing very new work where we can receive data from satellites in 3 different bands simultaneously: S band, X band, and Ka band. And these are some work which are basically got a specification and a request from Vikram Sarabhai Space Center for designing some antennas for reusable launch vehicle, and also we satisfied those ideas for them. Coming to the outline of today's presentation, I'll be having a very brief introduction to metamaterials, and then I'll be talking about some small antennas for metamaterials, and then some of our work on gain enhancement technique, and then a significant part that we have contributed probably first time in realizing a new kind of concepts in designing frequency notch ultra wideband antennas, then multifunctional ultra wideband antennas. Then I'll be going to some future directions if time permits. So I apologize if I am repeating some of the slides, because very recently I was at NIT Trichy, where there was a DST Spark workshop on completely on metamaterial for whole week, and there I had 6 hours of presentation on metamaterials, where I was very slow, and I in fact divided the presentations in 3 hours and 3 hours. So if some of those candidates are attending, then you might see many of the slides are being repeated over here. Okay, coming to the introduction, as you know, the boost or the spark in metamaterial research started around 1996 and 1999 by Professor Pendy, and then first experimental realization was by one group by Professor Smith, and then almost in the same time Professor Kalos and Ito also showed another complementary idea of realizing the metamaterials. As all of you know, that the term meta means something which is beyond the universe meta. And but if you go into the history and if you try to dig into the details of the the chronological order of what happened in terms of the advancement in metamaterial research, then actually the history dates back to 1968, and that was a seminar paper by Dr. Veselago, the Russian physicist, who actually first conceptualized, not realized, conceptualize the fact that if we have some kind of materials which will have exotic properties, maybe not necessarily the metamaterial means it has to have both mu and epsilon negative. This is a very common misconception people are having. We can have different kind of materials. There is called epsilon near zero material, mu near zero material also, and then we can have single negative material which is called ENG, epsilon negative or mu negative, and then one class is the double negative material. So please be aware of the fact that metamaterial doesn't always mean it is double negative. Anyway, coming back to the history, 1996, the first experimental work by Professor Pendy. In fact, first structures was proposed in the form of splitting resonators. Then Pendy proposed a new kind of structures. Then Smith's work, and then around 2000 onwards, there has been plethora of applications of metamaterial for realizing different kind of passive components, mainly the micro passive components with reduced size. We call it miniaturization, miniaturized applications. You will see different kind of power divider, then different kind of phase shifters and other kind of passive components have been designed. And then around 2007 and 8, Professor Zilkowski, Professor Lengetha, and few other Canadian groups also started contributing and metamaterial inspired antennas. And some, incidentally, some of the groups in India also are one of the initial groups, and then Professor Srivastava, and now I see many other groups who have tried to do different kind of work on antenna applications. And some of the groups are concentrating mainly on absorbing applications or polarizing applications, whereas we have concentrated more on the antenna applications. So I'll skip this part. Probably this is very fundamental, and probably some of also will be talking about that. The if you as an engineer, you need to understand the physics also. So for that you have to dig into the details of the thing. So if you see the classical physics, then in according to Drude-Lorentz model, you can have some material, you can create some artificial lattice where you can have array of wires, and then you can have epsilon negative below a plasma frequency, which is can be called as a plasma frequency. Below the plasma frequency, this type of arrayed structures can give negative epsilon. And in fact, this is not very new, because if you go into the conductors, especially the the concepts of dispersion, the normal dispersion, anomalous dispersion, and there is something which is called the radiation damping. So if you go into of the radiation and go into the details of Drude-Lorentz model, then you will get this kind of concept from classical physics also. Something is completely new. And then this was the Pendy's proposed structures, that if you have a pair of C-shaped structures oriented in a diametrically opposite fashion, and then excited by axial magnetic field, then you can have a narrow window across which you will get a negative value of mu. So this is a kind of conceptual diagram. This kind of arrayed structures, if excited by electric field, which will be parallel to the orientation of the wires, then you get a epsilon negative below certain frequency, which we call plasma frequency, and such orientation of the split ring resonators and then excited by magnetic field, which is orthogonal to the plane of the resonators, you get a negative epsilon around certain frequency range. And if you can cluster or amalgam these two particular concepts, then you can actually get a region, a small window across which both mu and epsilon can be negative. So this is a very popular slide. Many people shows probably, especially in introductory courses and stuff like that. If you have both mu and epsilon, and suppose you have different combinations of their values, I mean, considering that both of them can go to positive, negative, and the real part, imaginary part, all those factors are also there, of course, then you can actually have 4 quadrants, and you can think that this is forward propagation. We call it right-handed materials, and this is called epsilon negative material, which is the second quadrant, and the fourth quadrant is mu negative material. And because one of the parameters are negative, so as you know, the propagation constant k equal to omega root mu epsilon gets imaginary, and thereby these two particular situation probably won't allow any kind of transmission. So this kind of thing can be conceptualized for absorber kind of applications, whereas if you have both mu and epsilon negative, then you basically get a backward wave propagation. I will show this particular thing through a small animation that some of my students made, especially for the beginners. And some optical people are also exploiting the properties of the metamaterial. So if you have a conventional materials with refracting index greater than 0, and in between you have a sandwiched layer for which the refractive is less than 0, then you the Snell's law. So the light which is supposed to go, either away from the normal or towards the normal, but in this direction with a positive angle into the second media, it won't behave like that, but rather it will go with a negative angle, which is coming from basic 10+2 physics, which is Snell's law. So there you can say the reversal of the light, and this type of concepts have been used by different groups for realizing super lenses and stuff like that. So I talked about 2 different approaches of designing metamaterials. One is the resonant particle approach, which was pioneered by Dr. Pendry, then first experimented by Smith and some other groups, and then there was a parallel approach, or I can say another approach of designing metamaterials, which was transmission line based, where the initial contributors was definitely Professor Ito and his co-worker Dr. Callows at Ecole Polytechnique Montreal. And then if you see there, these are the salient features. So these are consisting of sub-wavelength wires and splitting resonators. Of course, these are narrowband structures, and there will be quite a bit of loss due to their resonant nature, high quality factor, of course. And there was a conflict between the two groups, and these particular groups transmission line based approach is very simple if you think physically. As you know, if we have a physical transmission line, and if you try to represent the transmission line through an equivalent circuit, then normally in a lossless transmission line you will have the series inductors and shunt capacitors. But artificially, if you can induce the complex, the conjugate component, that means you have a capacitor in the series arm and the inductor and the shunt arm, then that transmission line is called a meta transmission line, which is not evolving naturally, but you are using those additional components as SMD components, and then you are trying to have those type of materials. So such an approach is called the transmission line based metamaterial approach. So as I mentioned, if you go into the very basics of the metamaterial, then you can, even starting from the Maxwell's equation and Helmholtz equation, you can prove some kind of the concepts which metamaterial people claim. So normally if you see the conventional material, then E vector, H vector, and the pointing vector, which constitutes always a right-handed triad, whether you call it a right-handed material or left-handed material. That pointing vector and K vector, that is the propagation vector, are in parallel. Whereas from this equation, if you consider both mu and epsilon and negative, then these two equations change like this, and then what happens is the pointing vector and the propagation vector, that is the phase, are anti-parallel. That means while the energy is going in that conventional direction, the phase of the wave is going in the opposite direction. So if an electromagnetic wave propagates through such a medium, instead of phase retardation, what you get is the phase advancement. So such a concept can be used to design zero delay transmission line. Suppose you have a normal transmission line where through which when the signal propagates the delay is obvious, then you have a metamaterial transmission line where you have a negative delay. So these two delays can be adjusted so that you can have something which is very exotic. We call it a zero delay kind of transmission line. So these are some of the immediate implications. Okay, so and some interesting feature you can get from the concepts of the time average energy density. As most of you know that we have the electromagnetic energy density. It has two components. One is the electric energy density, another is the magnetic energy density, and you can write it like this. But when you have a quasi-monochromatic wave, this equation you cannot directly write like this, but you have to express it like this. And as you know, energy density can go negative. So both of these two parameters are positive. And if you do a little bit of more mathematics, then you get a very interesting phenomenon, which is, I don't know, there is a bit of delay in my end also. I mean, for the next slide gets loaded. So what you can show by using these mathematics and this some Maxwell's equation and some physical concepts, the ultimate thing is that Vp and Vg, which are phase velocity and group velocity, for a double negative material or DNG material, you have Vp Vg less than 0. So it implies that the wave packets and wave fronts travel in the opposite direction. So this is a bit of mathematical interpretation I was talking about. Now, if you just consider this slide is for beginners, those who are going to start their work in this particular area. Suppose you have 3 layers of material. The first one and the you can say right-handed materials, and in between you imagine that you have a medium which is engineered. That means you have the option to create that particular medium as per your wish. That means you can make one of the parameters negative, you can make both the parameters negative. Then what happens is you get 4 combinations. So this engineered medium can have 4 different options, both the parameters positive, both the parameters negative, and one of the parameters negative, which will be on the second and fourth quadrant. Now just see as beautiful animation. You are launching a signal from this end, and in this particular case, as you see, without any hiccup, the signal reaches into the third medium because this is a DPS medium. But when you have one of the parameters negative, you see you are launching the signal over here, but the signal doesn't reach over here. Of course, this is a oversimplified simulation because we are not considering the dispersive nature, we are not considering the frequency dependence of this mu epsilon, but it is a very interesting in the sense the basic idea you can get when you have one of the parameters negative. As you see, the signal doesn't reach over here, and same thing happens on this particular case also. You're launching the signal from port 1, which is mu and epsilon is positive, you get nothing over here. And the most interesting part is the DNG part, where you see this quadrant, third quadrant, you have both mu and epsilon negative, and you see this intermediate layer, the signal is moving in the opposite direction as far as the whereas the energy is going in this particular direction. So this is actually the anti-parallel phase and group velocity. You can think, you just try to follow my slide. I don't know how it appears in yours because it depends on your data speed and all these things. Probably you can follow that it is going in the opposite direction in the third quadrant. So this is a small animation. So now I'll be going into the details of the work. So these are some of the different kind of split ring resonators, circular, square shaped and hexagonal shaped split ring resonators that we have used in our work. And I won't again go into the details of this work because these are some of the equivalent circuits. These are needed for designing this kind of structures, whatever applications you go for, whether you go for absorbing applications or you go for antenna applications. If you want to have a split ring resonator, you need to know how those are designed. So these are 3 closed form equations of different kind of split ring resonators that we proposed. One is the circular split ring resonator, this is a square SRR, and this is the hexagonal kind of structure. So this is available in some journals. So we got a lot of queries because many people actually faced problems in calculating the resonance frequency. So in our recent paper, one of our recent articles in IEEE transactions, we actually had an appendix session where we have actually shown the calculation in details because we used to get many even to calculate resonance frequency, they are facing different kind of issues because it involves a bit of complicated equations, the elliptic equations, and especially the calculation of inductor sometimes is quite tricky. So you can use these particular formulations from our recent transaction papers. So these are some different kind of applications that we have used mainly for antennas. These are different
Hello, sir.
kind of
Hello, sir.
medium.
Sorry for the inconvenience.
Yeah.
So sorry for the disturbance. Your voice is completely not audible, sir.
Jadab, can you hear me?
Yes, sir, but
Now, sir.
very slow. Now it's
Dr.
okay, sir.
Jadab,
Yeah,
can you
yes,
hear
sir.
me?
Yeah, sir. Now it's good.
Yes,
Yeah, in between
you
it
are
was
audible
very
to me
low.
also.
Okay. Okay. Yeah. So you may mute the people again. In between
Yeah,
means
sir. Sure.
1 minute before it was good.
Yeah, no, no. In between it's a very, very low.
Okay. 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 Maybe due to signal because I'm not doing any adjustment after that. Okay.
Yeah, now it's
Anyway,
okay.
I'll keep the mouthpiece here probably, then try to be a little bit more louder. Okay.
Yeah.
Yeah.
Okay, I'm
So these
muting
are
all, sir.
yes, please.
Yeah, I muted all.
Yeah. Yeah, so
Okay.
these are some kind of structures which are basically planar transmission lines which are loaded different kind of resonators. I'll be coming into some of the antenna applications for these kind of structures. And if you go into the details of our paper, then you will some of our articles, then you will see that the equivalent circuit concepts where the transmission line and resonators are, combinedly, used, replaced by their equivalent applications or narrowband applications. The idea is these resonators are loaded with the CPW medium and they are coupled by this coupling coefficient K. It is the basically the magnetic lines, I mean the magnetic fields of the propagating signals that is coupled with the split ring resonators, and this is the some equivalent circuit kind of approach, and these are some kind of results as far as the dual notch or the wideband notch SRR applications are concerned. So I'll be going into the details, little bit details of that particular wings of the research. But before that, I'll tell you little bit of introductory knowledge about the electrically small antennas and some of these bottlenecks in designing electrically small antennas can be mitigated by using the metamaterial inspired structures under the leadership of Professor Zilkowski and few other groups started. And as you know, the electrically small antennas, the main problem they face is the highly capacitive reactance. Whenever you have an antenna which will be electrically small, say lambda by 5 or lambda by 10 or beyond that, then then problem will be the matching and thereby very low radiation efficiency. But metamaterial group probably showed that some of the basic limits of electromagnetics, like the Chu limit, which was later on rectified by Professor Maclean, which should be called as Maclean limit, but still we call it as a Chu limit, no issues on that. So some of those inherent limitations can be mitigated by using the metamaterial inspired techniques. So this is the Wheeler's definition of a small antenna. We can call an antenna as a small antenna when Ka less than equals to 1, where K is the wave number and A is the radius of the smallest sphere within which the antenna can be surrounded. Okay, so this was a kind of limit. I mean, it is something like that you cannot design an antenna for which Ka will be less than equals to 1. And then Professor Steve Best rectified this definition, especially for antennas with circular polarization and antennas which is having PEC ground plane, say monopole kind of structures, then this definition should be redefined as K less than equals to 0.5. And the idea that metamaterial group imposed and rather applied while designing electrically small antennas was basically using different kind of structures to produce a mu or epsilon negative, so that suppose you have a small antenna, then you have to cancel these capacitive reactance by adding a inductive reactance separately, but and then as a result the feed structure of the antenna will be complicated. The first theoretical proposal by Professor Zilkowski was something like this: if you can have electrically small antenna which is surrounded by inductive nature of ENG shell, which is basically epsilon negative shell, it is highly hypothetical, but he proposed like this, then it can take care of the capacitive reactance due to its inductive reactance contributed, and thereby you can achieve the conjugate matching and you can get a good radiation efficiency from electrically small antennas. As far as the fundamental limits of the small antennas are concerned, these are the one is the quality factor and then bandwidth and the radiation efficiency. As you know, the quality factor normally but when you use it for antenna, then you have to define it in a proper manner, and the quality factor, overall quality factor of an antenna will be defined by something like this reciprocal relation: 1 by qt is 1 by qrad, and then qc, qd, qs are involved, where this is quality factor these associated with the conduction loss, this is due to dielectric loss, and these are the surface wave loss. So losses are there in an antenna. Also we will be having losses, but which loss is desired in an antenna? The p rad is the desired loss. We want the power to be lost in the form of radiation, not in the form of conduction loss or dielectric loss or surface wave loss. So these are some of the theoretical understanding. This is the chew, that you cannot design an antenna whose q will be going sorry, below certain limit. So that was the choose prediction, which is something like this, and this was backlist correction. So you can see there was almost a more than 2 decades of separation between timeline separation between the work of Chu and Maclean, and up to certain limit they converge, but beyond that the exact approximate limit is Chu and exact is Maclean. So Maclean's formula is more correct, and you have to use that particular formula. So you can see some of the work by Professor Zilkowski and other groups in terms of the electrically small antennas, using how the metamaterial concepts have been deployed in designing better electrically small antennas. This is something which I am talking from our work. Okay, so this is ELS, which is called the electrical line source, which is basically a small radiator, and if you design this type of radiator, then its radiated power ratio is very small, because it's basically, if you compare introduce a term PR, which is without metamaterial shell and with metamaterial shell, then this is the situation. Actually you have a source over here, and you have three regions. Region 1 is, and region 3 are free space mu 0 epsilon 0, and region 2 is basically an isotropic metamaterial shell, which is defined as epsilon 2 and mu 2, and incidentally these are tensors. So I have not gone into the details of this, because there is a lot of theory involved over here, but we have shown that if you can satisfy a structural equation, which is a by b is given by this, or mu phi 2 and mu rho 2 at the phi and rho component of the mu for the medium 2, and then m is a parameter which defines the order of the resonance, then you can show that this particular plot, as you can see, this is the power ratio, the radiated power ratio PR. You can see for certain combination of mu phi 2 and mu rho 2, you get a very high PR. So with respect to the standalone antenna, I mean, in compared to the standalone antenna, your antenna is giving a 14 dB of more power radiated by the same antenna, thanks to the structural resonance contributed by this particular type of metamaterial shell. And these are some other interesting results in terms of the variation of the length. If you vary the length of this metamaterial shell, double negative or whatever you call, you can see that it is not that much factor within a certain, I mean around a certain range of the length, the resonance you get, and you get a very beautiful radiated power ratio. This is another work which is basically a dielectric resonator. As you can see, the dielectric resonator is excited by a transmitter. Of course you have to match it, and then when if you put a metasurface lens with a certain distance, I mean above the dielectric resonators, I mean this is excited in a mode so that you have a broadside radiation, something like this, but in presence of this metasurface lens, gain of the antenna is enhanced by 4 to 5 dBi. So this work is being continued further, and here the main disadvantage also I have to tell you, that because these lenses are metasurface lens, so these are highly frequency dependent, so you cannot apply it for wide band antennas or ultra wide band antennas. Maybe you can design some dual band antennas, and then you can try to design a dual band metasurface lens also. And coming to the interesting part of the work, other interesting part of the work I just talked about in our journey on metamaterial using metamaterial inspired antennas in designing different kind of frequency notched antennas and multifunctional antennas. Some of those are having applications in the cognitive radio application. So this particular slide, basically I made this animation to give you some idea regarding the cognitive radios, because as you know, the spectrum is very limited, and the IEEE survey and another independent survey by industry under the leadership of Professor Rapaport says that primary users are not using their spectrum perpetually. Even if you are having a perpetual distribution of the spectrum, but that's not being used. So that is a underutilization of the spectrum, and being so many efficient utilization of the spectrum is of paramount interest. So what we should do is whenever the primary users are idle, we should use and allocate those spectrum to the secondary users. This is the very basic idea of the cognitive radio. It is something like Airbnb model of the, I mean, which mimics like the hotel business, but Airbnb is like if you have many rooms and if you are idle, some of the rooms are available, you can host to the some of the guests. So that is the idea. When primary users are not using their spectrum, it can be relinquished and it can be used by the secondary users. Okay, so we have designed some antennas which have this kind of features which can be very good candidate for some of this type of applications. So I'll take you towards that journey. So this is probably most of many of you know, because this is the ultra wideband antenna, ultra widebands, which is from 3.1 to 10.6 gig. And because there are some pre-existing users within this particular band, so you have to make sure that your antenna is not radiating over the narrowband signals which are present over here. So FCC defined a spectral mass that you can definitely radiate over the entire UWB band, but you can't radiate over some of the bands which are already preoccupied by the narrowband services. So these are, when you come to the UWB communications, there are some candidates, popular candidates, ultra wideband antenna candidates like spiral antenna. Then you have printed monopoles, and then antipodal TSA. I mean, one of the beautiful piece of work was done Professor Siddiq and Yahya Antar, a single antenna giving a bandwidth of I mean, from 400 megahertz to more than 12 gig. So these are very good candidates for ultra wideband applications. And then we have done some frequency notching and some other kind of applications on different kind of antennas. This is a slide which is probably many of you know that within the UWB band, as an example, I have shown two narrow bands occupying within the UWB band. So you need to design antennas which will be radiating over those frequencies. But that's not the end of the story. The main important part is, as far as the cognitive radio applications are concerned, you have to come up with multifunctional antennas. That is, a single antenna has to do the frequency scanning so that you get to know which are the frequency bands currently idle, and then you have to make sure you have a communicating antenna, and your secondary users will be communicating through the spectrum holes or the narrow windows which are available dynamically. So this calls for some special type of antennas which we call multifunctional antennas. So if you see the reconfigurable antennas, then you can see that frequency reconfigurable antenna, then we have pattern reconfigurable and other kind of reconfigurabilities, and these reconfigurabilities are actually achieved through some of these means, either electrical or optical or some other kind of mechanisms. So when you go to the literature of multifunctional antenna, this is the approach you will see maximum. Like you have multiple antennas, one will be doing for ultra wideband scanning, which will be basically checking that which currently idle, and there will be cluster of antennas which will be used as secondary antennas for the secondary users, and each of them are resonant at different frequencies, and there will be some mechanical rotation or some electrical actuation kind of concepts. So at a time, one of those radiators will be radiating by, this is a mechanical concept, so this particular section is rotatable, and as a result either one or two or one or n will be coming in touch with the feed line, and as a result that particular radiator will be communicating. Signal processing and other intelligence mechanism will be involved, because you have to communicate at a frequency which is idle, which is that information you are getting from the UWB section. And this is the overall holistic scenario, like you have power versus frequency and spectrum, from which you get an idea which are the spectrum holes currently available. So as far as the basic block diagram is concerned, so this is the overall scenario. You have a sensing ultra wideband antenna and the reconfigurable antennas, and that is called as the heart of the cognitive radio antennas. So over next 5 to 7 minutes, I'll take you to this particular journey, that we have ultra wideband antenna, how we can make it frequency notch, how we can make it multifunctional and stuff like that. So this is a printed monopole antenna which is called fat circular monopole. This is a CPW fed, but you can have microstrip fed and other kind of mechanisms also. But the beautiful part of the work is here you have just used a couple of resonators in the form of splitting resonators, which are basically metamaterial inspired concept. As I mentioned at the very beginning, these are not metamaterial. Please don't use the term, but you can definitely say these resonators are metamaterial elements. So you can probably mention these antennas as metamaterial inspired antennas. So these resonators, thanks to their magnetic resonance frequency, won't allow a certain frequency component reach to the antenna. So it is like killing your enemy before it enters in your premises. So you don't want a particular component of the signal to reach over here. So as a result, that antenna will not be able to transmit at that particular frequency. You might see other ideas where people will be putting different kind of defects on the radiator or on the ground plane. That also will be giving you frequency notches. But the beauty of this idea is the radiator and the resonators are independent, and these resonators are not directly affecting the radiation aperture of the antenna. So these are some of the salient features and uniqueness for this kind of antennas, and this is the fabbed structure. I mean, this part is zoomed structure, and this is the some theoretical calculations involved, as I mentioned earlier, for determining the size of the SRR so that you can get the resonance at a frequency you expect for. And these are the the S1 response of the antenna without and with SRR. As you can see, this is completely ultra wideband, and this particular case, when it is loaded with SRR, it is frequency notched ultra wideband. And you can see the surface current distribution. This particular case is at notch frequency, which indicates the antenna is not excited at 6.34 gig, whereas the antenna is nicely excited at other frequencies. I have some interesting videos, but I won't take the risk because the platform might not suit and there might have data connectivity issues. Anyway, so this is the radiation pattern of the antenna. Because you claim that antenna is ultra wideband notched, so you have to make sure that you comply the desired radiation pattern at multiple frequencies. So 3.16 and 10 gig, these are the frequencies which are not the notch frequency, but at the frequencies where the antenna is reading. So as you can see over the E plane, the antenna is having a directive radiation pattern, whereas in the H plane you have a omnidirectional pattern. So you have basically frequency notched ultra wideband antenna without any perturbation on the radiation pattern of the antenna. And this particular concept, of course, you can extend for designing dual notch or wideband notch or multiple notches, of course. So this is automatic extension of the work that we did. So you have another pair of resonators which is differently sized, and differently sized means it can be closely differently sized and but widely differently sized also, and that will be giving you a dual band or wide band notch characteristics, as you can expect from this particular work. And most interestingly, there was a breakthrough in 2015. I mean, when we were working on this particular area, we observed that the basic idea that when we have two pair of switches also on which will be connecting the signal line and the ground plane. I want to use the term short because shorter is used by low frequency engineers, the electrical engineers. But for electromagnetic engineers, a short is basically an inductor and maybe bit of capacitance also. So when we did this, that means the same antenna is loaded with SRR and shunt strip. The same antenna now gives you a narrow band response. So this is the configuration A, whereas configuration B, you had only the SRR where you get the frequency notched ultra wideband response. And another interesting feature is when the gaps are closed, the SRR gets converted into the closed ring resonators, and then you get back the ultra wideband response. So ultra wideband response is basically revoked when you use these SRR switches, SRR gaps closed by some kind of switches. Okay, so you please note down the questions. I see someone raised hand, but I'll be very happy to interact at the end. So note down your question, and I'll be very happy to clear all your doubts. But please don't interrupt in between. Note down your question, or you can send it in chat box or the way the moderator will be doing. Okay, so as you can see, the same antenna, a printed ultra wideband antenna, when loaded with different combinations of SRR, shunt strip, and closed ring resonators, you get different kind of antennas: the ultra wideband antennas, notched antennas, and the narrow band antennas. And this is the scenario. Okay, and as I mentioned, because this antenna gives you two complementary responses, you can actually use them for sensing ultra wideband antenna as well as reconfigurable antenna. And these are the frequency response of the antenna. As you can see, this particular case, like you have two different complementary SON. One case is indicating notched UWB, and another case it is indicating a narrowband response. At the same time, by changing the dimension of the SRRs, you can make the SRR resonant at different frequencies, and then by you can have a narrowband communication at different frequencies. Of course, once the design is done and it is fabricated, you cannot change the SRR dimension, but you have to do some electrical changes in terms of loading some varactor diodes or stuff like that to change this resonance frequency and thereby actuating the narrowband tuning. Okay, this is a conceptual proposal. We have done that particular work also later on. And this is the gain profile of the antenna for two configurations, configuration A and B. As you can see, in one case, the antenna is giving a sizable gain over the entire band, excepting a sharp fall at the notch frequency, whereas in the second case, you see the complementary antenna response. So this is some additional information as far as the dual complementary response is concerned in terms of the some time delay responses and some additional extension of the concepts. As I mentioned, the beauty of this idea is it can be immediately applied to any printed antennas. I mean, monopole is not only the only printed ultra wideband antennas, but you can have tapered slot, you can have other kind of antennas also. In fact, we have shown that this concept nicely works even for horn antennas. These are some dielectric resonator based antennas. The bluish color is actually the dielectric resonators over here, and you can use the same concept to actuate such multifunctional responses. And I was mentioning later on that this idea later on you have used on a tapered slot antenna, which is basically antipodal tapered slot antenna. In this antipodal tapered slot antenna, for two different orientations and positioning of the SRRs, one near the aperture and another close to the microstrip section of the feeding structure. So because this part is the microstrip and then it goes to coplanar strip line, and then you get the transition or the tapering done. These two are on two different plates, the brown and the light brown, you can say. Okay, so these two, both the configurations, you get very sharp notches around the SRR resonance frequency. And then we showed that these concepts can be used for by putting multiple SRRs and multiple switches to use triple notched config to get triple notched configuration as well as triple narrowband configuration. So this is some work related to that. You may see this particular slide with great attention. Keep your attention over here, the point I'm taking my mouse to. So current configuration is frequency notched ultra wideband response because the monopole is loaded with a pair of resonators. Now, as I bring a couple of switches over here, pair of switches over here, the same antenna now becomes a narrowband antenna. And as the switches are toggled, on off, you get the antenna responses also toggled between frequency notched response and ultra wideband. Can be supported by proper signal processing and all. It will be a very useful antenna in this particular direction in for some of the models of the cognitive radio, because under cognitive radio we have overlay model, underlay model, and so on and so forth. So you can use this particular concept. So these are the experimental verification with initially using the copper switches. I mean, when the switches are on and switches are off, and with the different orientations of the split ring resonators, we have verified these concepts. I'm not going into the very details of this kind of thing. You can see these things and follow these things in our paper later on. And as you can see that using the surface current distribution and other kind of stuff, you can prove the point that I am talking about. Okay, so in this particular case, as you can see, you have NB1, NB2, NB3, narrowband 1, narrowband 2, and narrowband 3. This is actually we call it rectangular contour plot, which is basically the pointing vector. And this is frequency and this is the distance. As you can see, for NB1, NB2, and NB3, filtered energy enters the antenna. Some additional extension of the work using the dual layered structure or multi-layered structure, not using the SRRs just on the beneath the resonator, but also above the resonators as well. So this actually helps in reducing the size of the feed line, and thereby you get an additional layer also where you can place your resonators. And this you can go further details in IEEE paper that we published using this concept, and thereby there are some equivalent concept approach over here also. Okay, so this is the feed line part and this is the resonator part. Using these tools, you can actually the multifunctionality I'm talking about. Interesting part of the work in terms of the practical realization. These are the switches, practical RF switches in terms of pin diodes. we are also doing with RF main switches and other stuff like that. So these are the resonators and these are the switches, and this is the bias T arrangement and all for actuating and giving the bias. And this is the practical diode model SMP0402. This particular part of the experiment was done at RMC lab and with the support of Professor Frandafar at Queen's University. And again, I have interesting video, but I won't go into that of details of. So this is the diode off and diode on condition, S1 run response. As you can see, in one case it is a notched response, in another case it is a narrowband response. And similar profile is verified by measured maximum realized gain response also. And this is the experimental setup. As you can see, as a first experiment, we proved the concept for a filter. As you can see, this is going to the two port of the VNS, and this is the DC bias arrangement, pin diodes loaded over here. And the bias T in the first experiment, we use the inbuilt bias T of the Keysight vector network analyzer. And this work very recently we published. Initially, we published in IEEE WPL, and then recently we published again in the detailed work in the IEEE Access. And then this concept was recently extended by one of my UG students. I repeat, UG students, undergraduate students, BTech students. He actually realized his own thought process into a reality. I mean, using this type of rack and pinion arrangement, he actuated the motion of this superstrate, which is loaded on the antenna, and by different actuation of the SRR cell, the CPW line, and also the switches, he realized the antennas, which will be mechanically reconfigurable into different frequency notched as well as narrowband responses. So this is the summary of his work, where this part is the superstate and this is movable using that rack and pinion arrangement I talked about. And there's actuation happened through this microcontroller. I mean, through this microcontroller, which is biased through this USB port of the computer, the laptop computer. And this is the overall arrangement. A small motor, my 10 gram or 15 gram kind of motor, which is loaded over here. And this teeth, the repetition, the frequency, all these things he himself designed. A undergraduate student who is currently working at UR Rao Satellite Center. Anyway, so this is extension of the work, which is also again published in IEEE Antennas and Propagation in 2007. This is the summary of the work. As I said, ultra wideband antenna and different kind of loadings to actuate the motor and the microcontroller and the switches also. So you get the tunable notched UWB function as well as tunable narrowband function. So at the fag end of my talk, probably I'll need another 10 minutes. So do I have another 10 to 15 minutes, Dr. Jadhav?
Yes, you have, sir. You have.
Yeah. Thank you. Thank you. This is a very recent setting and other audio setting. So this is the extension of some of the, it's again not metamaterial but metamaterial inspired, because these are near field resonant particles, step impedance resonator loading on a monopole antenna. You have two different kind of SIR with differently sized, and those we have used for 5G applications, the millimeter wave 5G applications, the 28 gigahertz and 38 gigahertz. This work is at initial stage. Very recently, we have reported in IEEE 5G international conference in Bangalore, which will be happening in virtual mode soon. So probably this part is not visible. I have placed this one over here. So this is at 28 gigahertz and this is at the 38 gigahertz. And this is due to the excitation of these two SIRs, which are differently sized. So one is giving the 28 gig, the larger one, and the smaller one is giving a 38 gig. And later on, this is used in a MIMO configuration for checking the envelope correlation coefficient, and other work are in pipeline. Okay, so this can be a very beautiful candidate 5G applications. This is some initial results only I showed over you, and this is the summary of my talk. But as I mentioned in my title, I'll take some future directions like metamaterials. I mainly emphasized on the antenna applications. I'm sure that there are other speakers who will be probably highlighting other applications, probably some of the absorber applications, tunable and active absorber applications. I know some of the Indian groups have done very good work, so they will be talking on those things. And then other thoughts definitely, but I want to give you some future directions as far as the metamaterial antennas are concerned. One, just I talked about the metamaterial inspired antennas for 5G applications, and of course, I mean, these are the the unit cells you are using. The beauty is these are electrically small, these are sub-wavelength resonators, so if you can make their radiation efficient, then you can definitely use them. We have done some work in terms of wireless power transfer. There also we are in a stage of using the metamaterial concept to reduce some of their dimensions. And one wing of research is coming into picture. Government initiatives is also there. Energy harvesting, RF energy harvesting. Very recently, probably few of you have attended. There was a workshop by NIT Shilchar, which was an Indo-Canadian workshop. So there are a few speakers who talked about these different kind of energy harvesting applications. As far as metamaterial structures are concerned, they might be very, because you are already using them for absorbing. You're using them for absorb, different kind of absorber and shielding applications. But why not for harvesting applications? So some of my students are working in this particular area, and then terahertz antennas also may not be exactly antennas, but in terahertz also there are some applications in the metamaterial domain. So as I mentioned, in as far as the terahertz and research is concerned, so these are the different components. I'll not go into the very details, just I'll give you some summary. So this is gap is called the terahertz gap, where you don't have the proper sources. So you exist here, you exist here also, but in between you have a gap which is called 1 to 10 terahertz. So there are two approaches. One is either going up from using the solid state sources, which is gallium nitride impads and the GaN and other kind of structures. So frequency multiplier or some kind of concepts where you can go from microwave to millimeter wave and then to terahertz. Or in the optical domain, you have the optical technologies, mainly the physics people work here. From there, you can try to come down. So these are the different terahertz generation principle. And in some of the work, if you see, the metamaterial ideas can be very useful, especially for focusing the terahertz beam to coming up with a highly directive beam. So these I probably just will give you some idea regarding how these terahertz antennas, photoconductive antennas work. I mentioned earlier probably that you have a femtosecond laser pulse that excite the semiconductor substrate. You have photons converted into electrons and holes, which constitutes a transient current, and that transient current causes a radiation, and that radiation goes in this particular direction. Incidentally, because it is going from a semiconductor, so Dr. Please take care. So you have a lens, you need a lens over here so that the beam can be focused, because the terahertz signal is reaching from the semiconductor to free space, where there will be obviously defocusing of the beam, diverging of the beam. So you can use some metamaterial lenses, good quality lenses, to converge the beam. So immediate applications that can come definitely, because we have done work and we know that some very high quality lenses are needed for collimating the beam. In our work that we have designed, we used some BATOP lenses which we procured from Germany, and then we tested at ISAR, and some of the testing was done at SAC also. So this type of lenses, designing some high quality lenses for beaming, the collimating the beam is very important. And as I mentioned, RF energy harvesting, it is all about rectenna, which requires the matching, and then the power management unit and other stuff like that. But instead of antenna, we can have metamaterial based, metasurface based structures by which also you can harvest the energy. And this is some work, the glimpses I am showing actually from our work from the dielectric resonator based SCR. Some people, please, if you are in front of your system, mute yourself, please. Otherwise, I request Dr. Jadov to take care. So these are dielectric
Yes,
resonator.
I muted. Just I
Yeah,
think
yeah,
I'm muting all once again.
yeah,
Yeah, you just mute all.
yes, yeah.
You
Thank you.
unmute yourself.
So yeah, I'm audible.
Yeah.
Yeah. So because I am presenter, probably you can't mute myself. Okay. Yeah. So I am not actually unmuting myself. Yeah. So this is dielectric resonators and this is split ring resonators. Very demonstrated that a near field wireless power transfer is possible, and the biomedical applications, and the, as you know, the some of the smart electric vehicles are coming up where these wireless power transfer mechanism will be there. So these we have experimented also But these split ring resonators size, I mean sorry, split cavity resonator size can be reduced by doing different kind of metamaterial loading or magnetoelectric kind of loading. So these are some thoughts which immediately came to my mind. These I am showing from some of our recent work actually. So where we have the two dielectric resonators and one split cavity resonator, and the interaction, it is like a coupled system. Interaction gives rise to three modes, which is bonding, non-bonding, and anti-bonding mode, and these are the associated resonance frequencies. We have shown at this particular mode, that is the non-bonding mode, you can have a transfer efficiency which is close to 80% or above that. I mean, this is a small experimental setup. As you can see, this is the split cavity, and these are the dielectric resonators which are loaded like this and excited by the loops, because the proper excitation of the DR mode, which is T001 mode, and the SCR mode, which is T001 mode, is very important. So we use the loop excitation, and this is the overall experimental setup. As I talked about, probably you can see, you can go into the details of the paper. So there are three resonances, which is called the bonding, anti-bonding, and the non-bonding. And at non-bonding, you get a very high transfer efficiency. But this particular work can be extended. We are in the process of that. Whoever is interested, can think in that particular direction. I wanted to just give some impetus. So these are more details as far as that particular research is concerned. I mean, these are our work which we presented in Montreal in Wireless Power Transfer Conference, which is a focused MTTS conference in 2018, and very recently in Journal of Applied Physics, wireless power transfer using dielectric and split cavity resonators. So with this, I am at the end of my talk. Just some advice for the youngsters and the young researchers who are present over here. From my journey, I can just probably tell you these 2-3 points that don't solve irrelevant problem. When you're starting your journey, research journey, it is very important that you attack a proper problem. Don't come up, try to solve a problem for which a better solution is already existing. So we in our research group tell sometimes like this: don't propose a new big sword to cut the bread and the slicing the bread. So don't tell I have a robust technique slicing the bread, because sliced breads are already available, or you can have a small knife for slicing. Don't come up with a sword and claim I have a very robust technique by which I can have a better efficient method of slicing the bread. And then also sometimes some people make some crazy claim that I have done this, but that has no applications. It is something like that: I have an elephant which can move backward. What is the application? So always focus your research considering the research goal, and then only you will come up with something meaningful, because that is that is the need of the nation. And don't get obsessed with a particular concept or idea or laws. When some kids are learning the unitary system, if you ask this problem, I have applied this experiment, done this experiment. If you ask a 1 year cow has 4 legs, how many legs a 2 year cow will have? A guy who is just learning the unitary concept, he will probably say 8 legs, but that's not the idea. I mean, because you are not thinking conceptually, or from the real aspect. So be very precise and be very open minded while thinking and fixing problem, and take while thinking, and don't get obsessed with a particular law, because that might give you some papers, but that doesn't have any practical sense. Okay, so don't think like chatur. You use your effort in a proper manner, but think like rancho, so that you can come up with proper output, proper output, because we need research contribution which will have applications, which will be implications, because now government of India is also in a mission of make in India. So unnecessarily producing junk is not always required. I am telling because I understand that there are many youngsters who are attending this particular talk. So with this, I am at the fag end. These are the people which I am very indebted to. I have met very beautiful people in my research journey. My professor, then some other people, Professor Yahya Antar, Dr. Gautam Chattopadhyay, Dr. Ashin, with whom also we have worked on metamaterial inspired antennas, and then some other people like youngsters, and some of my foreign collaborators in wireless power transfer area, especially Dr. Samit, Dr. Devjit Sarkar, Dr. Shomok, and other people. So with this, I conclude my talk with a tribute to the real heroes, not the real heroes. I repeat, not the real heroes, but the real heroes who are protecting our country, the COVID warriors, and the farmers, the cultivators, the teachers, of course, and the mechanics, are the people, and the space scientists also, who are I mean the defense forces who are protecting our country in all fronts. So these are my honest acknowledgements and to all my collaborators. Okay, and with this I conclude my talk. These are the students and this talk, as I told, that this is a long journey, so you will see a lot of the stuff that I talked on was very I covered a lot, so I was not going into the very in depth in many of the things. So I advise you go into some of our papers to get and fetch more information, and also a very and Francis, which was authored by myself, Professor Siddiqui, and Professor Yahya Antar. So with this, I conclude my talk. Thank you very much for now to interact. Thank you very much. And again, thank to the organizers.
Okay, thank you, sir, for such a nice talk. And now I'm taking the questions received from the yeah. So first question is from Sheikh Sultan. When CSR
I I am hearing you twice.
how is CSR
I am hearing you twice. As a result, I hear the echo. So can you please repeat the question?
yes, sir. When CSR are
Yeah.
placed below the substrate, how is the CSRR connected to the patch?
Okay. Is it related to the work that I presented, or it is a general question? I am not, because
General question, I
I
think.
didn't anyway. Yeah. So I'll address this both the aspects, because question is not very clear to me, but I'll cover both the aspects so that the actual aspect of the person along with what I am thinking. So one is the SRR and another is the CSRR. So in the work that I was showing, those are not CSRR, these are SRR. These are parasitically excited by the field which is proper. And when you are using CSRR on a microstrip patch, I don't know how you use it in a microstrip patch or on an ultra wideband type of antenna. You have to place it in a way, in a location where it will be maximally disturbing the current if you want to create a frequency notch kind of application, because you want to kill that particular component of current which is causing the radiation of that particular frequency. So if you want to kill that one, you have to place the CSRR in that particular direction, be it in or be it in antenna. As far as the microstrip antennas are concerned, as you know that if you have a grounded microstrip antenna and if you excite whatever excitation mechanisms you are having, normally you will have the full ground plane, and the current in the ground plane is actually the mirror image of the current that you have on the patch. So you can place it on the ground plane with proper orientation, so that the incoming field will be exciting the CSRR, and as you know, the CSRRs or SRRs are complement to each other. So considering all these points, you have to place, one is the placement, another is the orientation, so that the proper component of the field is aligned with the field that circulates on SRR or CSRR. Otherwise, sometimes due to the cross polar arrangement, actual resonance will not be excited. I hope I have covered whatever he has asked for. Yeah, that's it.
Okay. Okay, so next question is by Swagata Chatterjee. What is the distance between metasurface and the antenna in terms of length?
Yeah, that particular one, it is close to lambda by 4 kind of thing, but you have to do some optimization, because ideally metasurface is big structures, but it's ours. I mean, for any applications, it can never be fully periodic, because you have to somewhere you have to terminate it because of the size. So it was a little bit of tuning after using the basic law of quarter wavelength kind of thing.
Okay, so next question is by so metamaterials are only double negative or single negative. Also can be called as MTM.
Yeah, this is a very good question. Firstly, as I mentioned at the very beginning, there is a misconception. Means people think it is no. We can have epsilon negative, we can have mu negative, and we can have neither of them as negative as also. So those we call mu near
So
zero or
your
epsilon
voice
near
is just
infinity.
become very low.
Yeah, is it better now?
Yeah, it's good.
I don't know what's happening today because I have used the same system and same audio setup for so many talks and so many classes also. Anyway, so if I understand the question properly, the confusion is regarding the double negativity. So yeah, double negativity is one of the subclass, but double negativity is not the absolute requirement for metamaterial. We can have a single negative material. We can, as I was showing in my animation also, and some of the applications, you have only mu negative, or you can have only epsilon negative, or you can even have neither of the parameters negative. Those also might be meta because those are also not naturally available. So you can have, for example, mu near zero, applications. It's not about, my advice need not be very crazy by negative thing. We have to think in terms of applications. Okay, so all the four components I talked about, along with that mu near zero or epsilon near zero, can have applications in different scenarios. So yes, in a nutshell, double negativity is just one of the subclass, but there are other classes of metamaterial also.
Okay, so next question is by Mr. Amit. What is the aperture efficiency of these type of antennas?
Which type of antenna? I talked about
Means,
quite a
there's
lot.
only
Yeah, probably I have to assume the next part. So yeah, so the type of antennas for which I was showing the application few times, if I mention. Yeah, so one was the monopole, which was loaded with different kind of resonators. And then we showed on some dielectric resonator antennas and then tapered slot antennas. So the efficiency remains unaltered because our mechanism is tuning on the feed line. Okay, so you can see the efficiency remaining unaltered. If I remember correctly, I am hearing echo. I don't know why. The efficiency reported, it was close to 90%. It was close to 90%, but we have to check for other antennas. But definitely it will give, it is not going to have much implication. And that's the beauty. That's the beauty in, if you see some of the other people who have used this kind of structures for frequency notching and all, they have defected the radiator. So this particular technique doesn't defect the radiator, and thereby very less chances of radiation efficiency getting sacrificed. Yes.
for DRA based on micro antenna for wideband applications.
Which, please, that first part I missed. Which technique or which thing is more suitable? Which material? Okay. Yeah. It again depends on the type of DRA. If you want to have very wideband application, are you having two devices, Dr. Jadhav?
No, sir. One.
I don't know. Yeah. So if you want to have a very ultra, then you can use the monopolar type of feeding, where the monopole will be exciting the DRA. The one I was showing, that was aperture coupled, because the microstrip excites the slot and then that slot excites the DRA. So it again depends on the application. All the feeding techniques are quite useful. The other one I was showing for the meta surface lens application, here it was simple microstrip feeding. So all the techniques are useful depending on the situation, depending on the application. We have to employ.
Hello, sir. Are you getting my voice?
Yeah, I was not
Yeah.
getting.
Okay, so next
Now I
question.
can hear again.
Yeah. Okay, next question is, please explain the concept of closing ring resonator in slide number 57.
Yeah, very good question. I really appreciate this one. Yeah, I was, very fast on that particular part. So, split ring resonator has very high distributed capacitance. Why? Because if I go to that slide, probably I have to share it again. Good that you remember the slide number. It was 57, right?
57. 57.
Do you see the slide again?
Yeah, now I got.
I'll go to 57. Yeah. Before going to 57, yeah. So this is slide 7. So yeah. So you see, I'll try to annotate on the screen for your better understanding. I hope I can do that. Yeah. If you see this particular part, anyway, so it's not allowing me to annotate for the time being. So this particular part, probably it's working, and this particular together constitutes capacitance. So these two capacitance are actually in series. So this capacitance, is my annotation visible?
Yes, sir.
Yeah, these capacitances are like coplanar strip line capacitance, and it can be modeled the way we model a coplanar strip line capacitance, which are two metallic line which goes parallel to each other substrate. And these two together forms distributed capacitance, and that's why we represent the equivalent circuit like this. We have this, we have this, these are the two capacitance, and then sorry, and then we have an inductor over here. This is the equivalent circuit of the SRR. Then we have modified it also. But when you close this ring, this distributed capacitance which comes between this half and this half is doesn't come no longer in that manner. Simulation also. Interestingly, this resonant frequency doesn't fall UWN from 3.1 to 10.6 gigahertz. As a result, this CRR, as you see over here, doesn't have any notch, and it gives you the UWB response. Okay. So closed ring resonators resonance frequency doesn't fall 3.1 to 10.6 gigahertz, and that's why we don't see its effect. Or in a simpler way, I can say now the feeding line is transparent, fully transparent to the entire ultra wideband signal. Okay, that's the explanation.
Okay, sir. I think I can't take because it's approximately about to 12 and the WebEx is till 12 only.
Oh, oh yeah. So we are just on time.
Yeah.
Yeah, but
And
please
this,
share my email ID. I
sure.
probably again go to the last slide. This annotation is not probably allowing me. Anyway, my email ID is
Okay, I
cshaha
will
at
put in the chat box.
IEEE.org. Yeah, it is there already probably in flyer. You can put in the chat box. cshaha at
Sure.
IEEE.org. Feel free to ask any question. I'll be very happy to get back to you in terms of all the queries.
Yeah, I have put your mail ID on the chat box.
Yes.
Okay, sir. Thank you, sir, for such a nice session. You have started from the basics and you told about the different types of metamaterials, groups working on the metamaterials, different resonators, its types and formulas to design these resonators, as well as different types of metamaterials used in antennas to get the desired characteristics. You told about the complete antennas, controllable narrowband antennas, their equivalent configurations, reconfigurable antennas, mechanically tunable functional antennas, and very good practical overview of realized prototypes as well as the DRA. Everything you have told, and also taken so many queries. So I thank you, sir, for such a nice talk on behalf of IEEE Rajasthan subsection as well as APS chapter Jaipur and Government Women Engineering College, Ajmer. Thank you, sir, for very good session.
Thank you, Chinmoy Saha.
Yes, sir. Professor Sarma.
Yeah. Thank you very much. It was a pleasure to me. It had been a pleasure always for last 10 years or almost a decade now. Remember all the memories we had together in different conferences. Professor Sharma and then you people coming to Kolkata. Remember how the Antenna Week and AEMC, have gone very nicely because of your supports, wholehearted supports, and now it has taken a different shape or different name, but it is like 4G going to 5G. So thank you very much for your all supports over the years and nice initiative during this pandemic. Thank you very much. I really cherish all the memories that we had together. Yeah. Thank you.
Professor Sarma. Sir, you want to say anything, Professor Sarma?
Oh, thank you. Thank you.
Thank you very much. Thank you, to all the participants and also Mr. Puneet for, hosting this one initially, telling some comments about the metamaterial, and he was very, he was telling he'll be hearing the talk fully. So I appreciate my thanks to him as well. Okay. Thank you very much.
Okay, thank you. Thank you, participants. We'll meet next at PM again in the evening session. Okay, thank you, sir.
Thank you.
Thank you, everyone.
Yeah.
Okay, thanks.